Thank you very much. I'd like to welcome you to this discussion of high-efficiency power electronics. This is a very interesting topic, partly because high-efficiency power electronics appear on both supply and demand sides of the energy equation. So they are both inverters that convert DC from solar power to put it on the grid, and then, of course, they are at large utility scales within utilities, for working with AC power, and then we go AC to DC in lots and lots of different appliances that we have. I mean, I'm holding up here my favorite or least favorite high-efficiency power electronics. I spent a lot of time shopping for my light and highly engineered computer. I didn't get any choice in this 1 pound or so transformer. It's kind of the component that time forgot. And that's actually what we're going to be talking about today, because there's a huge transformation going on in the field of high-efficiency power electronics, particularly through new materials. And this panel is going to have a very interesting conversation about that. What's interesting about this also from the perspective of the whole 2 days discussion is that these components are, in a way, a case study of the difficulty of dropping transformational components into a system that's been designed to be resilient and effectively resistant to change. So there's some interesting sort of promises and pitfalls involved in discussing the incredible promise here. I'm going to quickly, I know that we're up against lunch, so I'm going to quickly introduce the panel and then just let them go. The first person who will be talking, giving us kind of a broad overview of the field and the research and what things might look like over the next 10 to 15 years if everything comes true, is Rajeev Ram. He is a professor in the Department of Electrical Engineering and Computer Science. He's also with MIT. And he served on the DARPA Research Council, and he also was a program director with ARPA-E. There's probably, I mean, he's just a fantastic resource to kick this whole thing off. The next person is Harikumar, who is the Vice President of Advanced Technology with Ingersoll Rand. He does strategic technology management for a $14 billion company. And the next person is J.B. Straubel, who is the Chief Technology Officer at Tesla Motors. He's also worked on electric airplane propulsion. With Tesla, he's working on supercharger stations, and apparently as a youth, he outfitted a Porsche 944 with an electric golf cart engine motor. Anyway, and also we have Umesh Mishra, who is a professor at UCSB in electrical and computer engineering. He's also the CEO and co-founder of Transphorm, which is a local company that's working on gallium nitride transformers. So with that, I'll turn it over to our presenters.
All right, thanks, Lisa. So now I'm back full-time at MIT after spending 2.5 years at ARPA-E. And so at ARPA-E, one of the things that I was responsible for doing was being the electrical engineer in the house. And one of the questions that I always got asked is, why does the Department of Energy really need to be funding power electronics? And that was one of the very first things that I basically tried to address. And so the argument basically has to start from just looking at electric power just in general. We know that if we take a big step back, that electrical power basically generates a large fraction of the greenhouse gases in the United States. That's primarily because of our reliance on coal. If we look forward, we know that the electricity sector is actually growing quite rapidly in terms of comparing it to the energy consumed in buildings versus the energy consumed in transportation, as we see a lot of those other loads basically turn towards electricity. Now, one of the things I'd like to do, just since I'm the first speaker in the panel, is actually just take a minute and kind of define power electronics a little bit. As a place to start. So I kind of think of the power electronics as basically being the transmission. It's the thing that fits in between the power source and the load. And so very much like you would have a car, it's really the transmission that goes in between the engine and the rotation of the wheels that gives you traction. And so systems that don't have power electronics, that consume electricity, are very much like cars that basically don't have transmissions, right? So basically things that you can always basically only have one gear that you're driving in. So imagine that you drove here to this meeting today, only driving in 4th gear. And you can imagine how that would improve, the impact of that on your fuel efficiency and your drivability if you only had one gear. Now it seems kind of far-fetched that if we've got electricity What kind of electrical systems do we have? What important loads are there that basically don't have electronics in them? And it turns out there's a large number of loads, and I think all of us have these loads in our houses today. So if we kind of look at motors without power electronics, these are motors that basically only have two states, on or off. They basically work in simple ways. So the compressor motor in your air conditioner is an example, right? You guys have all heard of the compressor go on, the compressor go off as you basically try to maintain a certain temperature. Your refrigerator does the same thing, and these represent some non-trivial loads inside buildings, right? A significant fraction of your building load. This also happens in industry, so process pumps. So there are a large number of pumps that the way you basically control you tie together the spinning of the motor to the movement of the fluid is basically with a gearbox. And so you lose energy in basically all the mechanical friction inside that system. And of course, my favorite example is a louvered fan. So if you're basically trying to dry something, instead of being able to have electronics that can change the rate that you actually spin the motor of the fan, what you do is you basically stick a louver on it to basically block the wind. And so obviously that's the least efficient way. So the idea of basically electrical systems that effectively don't have a transmission, that always are stuck in one gear, really is reality. It's a transformation that making these systems smarter, introducing power electronics is something that's been happening over the last 10 years. And so what does power electronics do? So we have examples of doing AC to DC conversion, DC to DC conversion in mobile devices, DC to AC for going from solar power back to the grid, the 60 hertz, and AC to AC for converting the rotation, the electricity generated by the generators in a wind turbine to the 60 hertz in a grid. So how do we kind of look, if we look forward a little bit on this technology, today about 30% of all electrical power flows through some form of power electronics, and that expectation is that more power will basically be flowing through some form of power electronics. Why do we expect that? And so we expect that because if we look at various sectors, so if we look at electricity, about a third of the electricity in the United States is consumed in residential, a third is consumed in commercial applications, business applications, and a third is industrial. So if we look at about 19% of commercial and residential is lighting, and of course we can see that we're going from a world where we've got incandescent light sources that has a filament that plugs directly into the electricity grid to smarter devices, moving to LEDs where you actually need electronics to convert from AC to DC. Today, really you basically would be hard pressed to find a power electronic chip that can high energy efficiently convert that AC into DC, and about 30 to 50% of the cost of a luminaire today is the power electronics. If we look at other sectors, so industrial, about 65% of industrial electricity consumption is the pumps and the motors, the fans that are inside that, and they basically represent a significant amount of the energy consumed in the industrial sector. And about 20% of all that energy in the United States is basically lost to some form of mechanical throttling, right? The examples of the gearbox of the louver. And then, of course, we're seeing other sectors that are actually becoming electrified. The best example of that is looking at electric vehicles and hybrid electric vehicles. And if we look today at buying a hybrid electric vehicle, about 20% of the material cost is the power electronics. It's the next thing after the battery, typically. So that's the inverter and the charger that's inside here. So you can sort of see why power electronics is actually becoming important. Now, historically, power electronics has been an area there's been very little investment for commercial applications. So if we look to the left, that's basically showing you an example of that power brick. It's a typical power density. This is a pretty good power density, 100 watt per cubic inch. And what we're showing on the right is an example of the same supply, 20 amps, research that we funded at ARPA-E. It's basically resulting in chip-scale power supplies. So innovation, because this is a gallium nitride on silicon technology, new magnetic components, new packaging technology, being able to do chip directly on package, and new circuit topologies, these coupled flux inductor topologies, allow you to basically get to 1,000 watts per cubic inch in a power supply, a dual-phase power supply that's smaller than a quarter. Right, so what we're seeing is basically making that, the power supply that Lisa held up, basically making that invisible, and simultaneously making it more energy efficient and easier to produce at large volumes. Another example is this is another project that we funded at APEI. It's a 5 kilowatt inverter, and it's an inverter that's basically about 7 inches across. And we see that in the relatively not too distant future, we can imagine something about the size of a deck of cards that can basically handle about 10 kilowatts of power. And so that basically means you can actually handle all the power processing needs of a large home or small business in the United States with an inverter that's about the size of a deck of cards. This one's actually about 97% efficient. It's a real device. It uses, again, wide bandgap semiconductors and novel magnetics to be able to realize that. And then my last example is actually being able to go to even higher scale. So this is a year ago, this was the highest voltage transistor that had ever been made. Another example of wide bandgap semiconductors on that fingertip is a 15 kilovolt transistor that basically can manage on its own about a megawatt of power. And so you can see that you can massively change the way that we manage the grid if we have electronics that are actually working at grid voltages. And today, these transistors are now working at voltages on the order of about 18 kilovolts. So what's the impact of some of these systems? If we look at this, we can take a 1 to 2 megawatts. This is sort of our picture of how the grid looks, right? It's a 35-ton of magnetics that are basically working at 60 hertz. There's almost no electronics inside that. If you basically add power electronics to this, you can basically up the switching frequency to 20 kilohertz. All of a sudden, your magnetics get smaller. Now your transformer is 450 pounds. You go a little bit faster with better topology, new materials, you can basically drop that down to 100 megawatts. So for those of you who were at the ARPA-E Innovation Summit in Washington, you saw several examples of systems, megawatt scale systems, that basically fit inside a suitcase. There were 2 of them that our researchers basically brought in the back of their cars as demonstrations of real systems that can actually handle megawatt in a modular sense that are on the scale of rack-mounted components. Now, of course, there's an advantage, and so the other thing that you notice is actually going from the 35 tons to the 100 pounds. Obviously, the system's getting cheaper because you're replacing the cost of copper and steel with higher performance materials, but much smaller volumes. But the other thing that's happening is the efficiency is increasing. The highest efficient device that I'm actually showing on this graph is actually the 50 kilohertz device. That's got more than 99% conversion efficiency through that power electronics component. The other thing is that now, whenever you've got power electronics, wherever you've got electronics embedded in your system, you basically have a chance to be able to couple that with controls, to couple that with algorithms, to be able to make your system smarter. What that means potentially for the electricity grid, if we kind of look out a little further, is that we can actually make it so that instead of a paradigm where all we do in terms of controlling the electricity grid is committing generation resources and dispatching generation resources, now all of a sudden the grid itself can actually become resilient and responsive. You can have a grid where you can actually route electrical power actively. If your transformer, not only does it become smaller with the addition of electronics, but it becomes smarter. It becomes a valve, or it becomes the equivalent of a router. And so you can imagine being able to make a grid that's more resilient. It's more resilient to fluctuating generation, right? For example, from renewables, you can actually route power over large geographic areas and basically average out those fluctuations. It becomes resilient to fluctuating demand, and more importantly, it becomes resilient with respect to failure, both hardware failure and cyber failure. And under a program that we had at Genie, under ARPA-E, this is something that's actually become a reality. There are examples of utilities throughout the United States that actually have demonstration projects to start deploying some of these systems. We have about 40 of these that are basically 40 of these kind of power routers going into active cabling systems in TVA. We have 5 of these going in at Southern Company, and these are going in for all the advantages that actually come with resiliency. So with that, I'm going to stop as maybe things that you could do with electronics, all illustrating wide bandgap, all illustrating new magnetic materials, and what the impact might be on the grid as well as on the load. Okay? Thank you.
Morning, everybody. I'd like to thank the organizers for having me here, and I really enjoyed the last 2 days of learning a lot, and I built a lot of new friends as well. So I'm here to share a few things on power electronics and air conditioning and refrigeration. Professor Ram just highlighted how this portion of the sector is a little behind in catching up, and we have some areas to catch up with. Ingersoll Rand as a company, it's a 14-odd billion listed company. We have multiple brands within Ingersoll Rand. Ingersoll Rand as a brand is in the industrial compressors and tools. In fact, that area has progressed pretty well in adoption of some of these power electronic tools as part of industrial processes. We also have Trane, which is an HVAC, air conditioning, heating, refrigeration company in residential and commercial applications. And we have Thermo King, which is a transport refrigeration company for moving large trucks and trailers and so on, as well as bus air conditioning. We have a brand called Club Car, which most of you might be in golf courses. Ironically, with no offense to Tesla, we are one of the world's largest electric vehicle making companies, but they're all on golf courses, and they're on deep lead-acid batteries, waiting for more innovation from people who spoke in previous panels and maybe in this panel on new battery technologies. And then, of course, we have Schlage, which is a security business which is really moving very rapidly into electronic transformation. So one common theme across a lot of these brands is the transformation from traditional mechanical company to an electronic and electromechanical and maybe even off on the web kind of company, which is what is happening to security, largely. And as we make this transformation, how does the culture of a company which is traditionally routed in mechanical design systems make that change? And what would be the need from the electronic innovators to kind of adapt in order to move the industry even faster? It's a wordy slide, but I'm just going to highlight a few points. If I look at the mega trends of what's happening, and we heard across the last 2 days, if we look at energy efficiency, which is clearly a focus area, and what implications does that have to HVAC, and more specifically into power electronics. So part load efficiency, and Professor highlighted about a compressor going on and off instead of adapting to part loads. And so part load efficiency is clearly an area which is driving and has a lot of implication towards power electronics, besides selling life cycle costs. So how do you sell that to a customer to say you're going to pay a little extra now, but you're going to save through its life cycle? It sounds very simple, but it's not very easy, and we'll talk more about that. We heard a lot about smart grid and demand response, and again, that's an area where electronics can play a huge role. And as we move on to financial situation, in fact, one of the aspects which I've been talking to multiple people, even here as I network, is the clear lack of engagement from banks and financial institutes. I live in the city of Charlotte. I talk to Bank of America very often. Of course, there are people who are engaged in the built environment, as we call it, the buildings and homes, but how the financial institutions can get into the whole game of retrofitting for efficiency is an area I'd rather call on the leaders in this room to kind of take that to a next level. As we move on to regulations, of course, that's an area which all of us are deeply engaged on through the area of refrigerants. And in fact, a lot of progress has been made in those component technologies to even move to things like carbon dioxide refrigeration, as an example. But from an implication to our industry, life cycle assessment is something which has almost become mandatory in our field. And so life cycle selling, again, back to part loads, is a very important part. Getting financial paybacks in areas. In fact, there must be people here from Berkeley, Lawrence Berkeley Lab, did a fantastic work in 2010, I think, on a financial model for building retrofits. And none of the districts in the US adopted it, but guess what? Singapore government is playing on that book by the page. And that's an area we have moved quite a bit in adopting power electronics in areas like Singapore, and clearly maybe areas in US have to catch up. Emerging markets in general, again, lifestyles are changing. You will hear more words on, power is not very clean. At the same time, food wastage is a very prevalent thing in places like China and India. So how do you do with minimal power or unclean power and still do a better job on food processing? Even adopting technologies from solar and other associated areas is critical. But there are a few challenges as we integrate it. And again, I was talking to some of the LED companies just now in a break. When you talk of lighting, you're closer to an end effect. Whereas when you talk of air conditioning, power electronic is a little backstream. And so the integration is a key challenge, be it in the area of reliability and robustness, be it in the area of lack of standards in areas like air conditioning, and integration development time becomes extremely high. Besides the rapidly changing choices in the motor technology and how these two are very closely interlinked. And the whole mindset of transforming from a mechanical design company to an electromechanical and software design company is something all of us will have to go through as a cultural change in managing this multiple life cycle of technologies, where a compressor might be a 15-year technology, whereas a power electronic might be changing every 5 years, the rapid pace at which we are progressing. And last but not the least, the specification terminology is pretty confusing, at least to a lot of engineers like me, when people use the word like VFD and VHD and inverters and static converters and all kind of stuff. Together with the lack of specification in the industry, it actually promotes a lot of chaos. And so I think it's time we kind of get back to basics of what means what in order to improve the adoption of these technologies. So in summary, the trends are surely very promising. There are a few challenges which we can surely overcome. And technology is, there's a clear hunger in the industry for disruption. And I'm sure, rest of the panelists and people in the room have some solutions for it. thanks for your attention. And I want to thank Professor Madhav and Mr. Dave, who educated me in this area to be in front of you. Thank you. Bye-bye.
Good afternoon. My name is J.B. Straubel, CTO at Tesla Motors. And certainly our perspective on this is transportation related, but power electronics in transportation and surrounding the transportation market actually goes quite a bit upstream as well when you think about chargers and then where that energy comes from. And I think many of you have probably already heard of Tesla, but we have several different lines of business internally. We're building and designing our own vehicles, like the Model S that a customer was kind enough to bring to the front of the show today, but also building powertrain components, so battery packs, chargers, drive inverters, motors, and selling those to some other companies like Toyota and Daimler. And I think it's important to always kind of step back and think, what is the real challenge that we're trying to do anyway, and why are we going after this? It's not because we think the world needs more cars, but it's mainly because we think the world needs a different type of sustainable transportation. And transportation is one of the biggest end users of energy out there, and it's also one of the most difficult to migrate towards sustainability. There aren't as many easy pathways to move solar or wind or small hydro or pick your favorite renewable, into the transportation sector. And that really is the long-term vision that we have. And I'm a little biased, but I think solar is one of the best long-term solutions. And we try and think in terms of what does a long-term system and whole network look like where you're moving solar directly to transportation, and what are the critical technology challenges to get there. And within Tesla, we basically have two areas of strategic innovation. There's many other smaller areas, and I'm sure there's a lot of engineers there that'd be frustrated if I boiled it down to these only two, but these are the most impactful. And energy storage is one, batteries, everything to do with batteries. And this field gets a ton of attention. It gets a lot of research dollars. There's many, many startup companies. It's really, I think, on the verge of being overhyped in some cases. It is, of course, still very strategic for transportation. The second is electric power conversion and control. So generally, that's everything surrounding power electronics. And it touches almost every part of our product in not quite so sexy and visible ways as a battery pack does, but the chargers that manage all the flow into the battery pack, the traction inverter that controls the motor, that's entirely what controls the feel of the car and how it responds when customers push on the accelerator pedal. Also, supercharging. This is a big new initiative we're focusing on to do faster DC-based charging, as much as 100 to 120 kilowatts off board the car. So that's very power electronics intensive. And finally, with integrating renewable energy, that also is really entirely dependent on power electronics and how it integrates into the vehicle. So these two big areas, and I think power electronics is somewhat underappreciated and underserved. Speaking kind of from our recruiting side, it's actually much harder for us to find very, very capable engineers and new graduates coming into the field that have great power electronics background and expertise. So I think it's an extremely exciting time for new students that are in this field already. There's so many opportunities. And maybe just to look at this a little bit graphically, to think about how power electronics plays into all this. They're really at the center of all the power conversions that happen in and around the vehicle. And especially with renewable energy integrating into that, anytime you make this transformation going from AC to DC, power electronics are involved. And in a vehicle setting, particularly any modern electric vehicle, you can't do that in a non-highly controlled way. Customers expect their cars to have incredibly fast response. They expect the charging to be smooth and not interfere with anything else that's on their grid or in their home. And all of that requires a lot of control and a lot of power electronics. And one reason that the efficiency here is so very critical, especially for electric vehicles, is because we send the energy through power electronics so many times. Professor Ram mentioned that 30 going to 80% of the total electricity generated goes through power electronics, but the electricity going into an electric vehicle, especially if it came from a renewable source, might go through power electronics as many as 3 to 5 times. So you have this sort of 3 to 5 time multiplier on that efficiency. 90% efficiency isn't anywhere nearly good enough. You've lost almost half of your power if that's the case. And if you look at kind of this flow of energy here, solar comes in as DC. It has to get inverted, so it can go back onto a grid. That's one power electronic stage. Then it either goes to the house or back onto the grid. Eventually it goes through a charger, back into the vehicle, stored in the battery. Then it goes through a drive inverter to get inverted back to AC to control the motor. And if you're driving around in the car and using regenerative braking, you might have a whole nother 2 transformations where the energy comes back through the motor as a generator, back into the battery pack, and then you use it again through the drive inverter. So that's a really, really kind of convoluted energy flow, but it's incredibly dependent on efficient power electronics. So these have to be high 9s. You need to be in the well above 95% to have sort of viable energy flows here that don't just eat up all the efficiencies in trying to have an electric vehicle in the first place. And just to focus on a couple of the areas that we look at for improvement, some of the most critical R&D areas surrounding power electronics, efficiency is definitely number 1. And it's not just because of the energy savings, but it compounds into a lot of other areas of improvement. And the second would be controls and software. Power electronics are integrally linked with microprocessors and the software that controls them. A transistor that can handle power isn't very useful unless you know exactly what to do with it. And that field is still evolving, and it's still really very young when you think of all the different ways that power could be controlled more efficiently. And the final really comes down to more materials challenges, pushing to higher operating temperatures, pushing to higher power densities, better reliabilities, lower cost. And those things are really targeted more at the device level, thinking of how do we do better material science and processing so that we can have fundamentally better devices that can be married with better control. So that's kind of a quick overview. I also, thinking about this efficiency compounding, this is one that, to me, I think isn't very intuitive to people, but efficiency has so many positive feedbacks, especially in a vehicle. And the first is that you can get higher power density. Something that's more efficient generates less heat, so it can actually be physically smaller without overheating. That's a nice benefit if you're trying to package it into a car with limited volume. You can also, of course, get longer range in a car. Batteries are really precious and expensive, so we want to make the best use of the energy that we store. So if we have a more efficient power converter using that energy, we can get a little bit more range or have a little bit smaller battery pack. That also can correspond into faster acceleration. If you have a power converter that's more efficient, you end up wasting less of that as heat, and more of it becomes acceleration or actual useful motion at the motor. On the temperature side, we also get lower device temperatures if it's more efficient, and that tends to promote higher longevity. So you end up with devices that last longer, end up being smaller, and ultimately cost a lot less. It's probably the most virtuous cycle of all the different attributes related to power electronics. So I think it's really key when people are trying to quantify the value or the true benefit of increasing efficiency a small marginal amount. You need to look at the end application and think of all the sort of positive compounding that can go around that. 0.1% improvement in efficiency in power electronics has a massive improvement for us. That's something we would spend a lot of effort and a lot of money to go after. So I won't take up too much more time, but I'll leave some time for questions. Thank you.
Hi, I'm Umesh Mishra. I'm a professor here at UC Santa Barbara and also CEO of Transphorm. And I'm the last after a beautiful talk, so this will go through quickly because I just wanted to set up a few things. Rajeev has done a fabulous job, as has Hari and JB. So anyway, so the heart of all power conversion actually is a switch. That's how we basically do power conversion. And the switch allows current to flow when it's on, holds off voltage when it's off. Now, I'll take the other tack. Actually, manual mechanical switches are very efficient. The switch on the wall is 100% efficient. But as Rajeev mentioned, it's either on or it's off. So if you add intelligence to a switch, you basically switch them on and off rapidly. That's how you add intelligence like you do in a computer or anything else. And when you switch devices on and off very fast, you end up actually having losses or things don't become as efficient as before. For that, go touch a dimmer switch on the wall. It'll be warmer than a mechanical switch, and a dimmer switch has some intelligence. So in my view, gallium nitride-based power conversion, obviously I'm the CEO of a company that does gallium nitride, so that's the answer by definition. Okay. And the answer, basically is, gallium nitride is a material which actually is, it's quite a remarkable material. It's the same material that's used in solid-state lighting, so it is now a very broad footprint, and it's low loss when it's on and holds high voltage when it's off and can be switched rapidly. So gallium nitride is basically what we're all about. I won't spend much time on this, but just leave it to, this is similar to Rajeev's slide, but what it says is that conversion losses basically uses up about 10% of all the electrical energy that is generated in the country today. And that's enormous, right? And that's equal to all the energy that is generated by renewables today. So it's like pissing away all the good energy that you have in just converting it to a useful form of energy, which is, we'll all agree, is not kind of a good thing to do. And so as we deal with this problem, I think there'll be multiple benefits, as JB mentioned. I'm saying Transphorm could, this is a slide I just snuck in, so anybody who does this well could reduce total energy demand by over 10%, which is $80 billion in annual energy cost these losses have to our economy, and 600 terawatt hours of energy is saved, which is 500 coal power plants equivalent. So this is, imagine just having 500 coal-powered power plants just turned on to supply losses, okay? It doesn't do anything, it just supplies losses. Pretty nasty stuff. So what is a terawatt hour, actually? And if you look at all these terawatt hours, they're in many, many segments, similar to what everybody said. Industrial motor drives, and that includes, by the way, the air conditioning and refrigeration aspect. That's huge. Data server power supplies, this is growing like crazy, both to do search and stuff like Google does, like what Oracle does, but also Facebook and social media, they all use massive server farms. Solar inverters, I agree with JB. I think solar is a very cool technology, and solar inverters actually play a critical role in the full system cost, significant roles now that panel costs are dropping so dramatically. And electric motor inverters, this is growing very, very fast. It's a small number now, but it'll become a large number in the future. So what are all these terawatt hours actually? And this is just a tongue-in-cheek slide, but it defines what a terawatt hour is in a way that we can understand. San Francisco actually consumes 6 terawatt hours of energy. New York City does 50. Vegas consumes 33 terawatt hours of energy. The whole United States, the Western United States, consumes 270 terawatt hours of energy. This is half the total energy we lose in power conversion. So you can imagine what the scope of this problem is. It's not sexy at all because it's hidden, as has been mentioned by Hari and others. It's a hidden thing. It's at the back, but it's what makes, we have to tackle it because it's so important for basically all aspects of the end result is multiple climate change issues, just size of the unit issues, as Lisa talked about in the beginning. But anyway, let's get to the brass tacks. Here, you can have a great idea, and how do you actually shove it into the market? Okay, that's very hard. I'm telling you from personal experience, it's very hard. Okay, and what you need is investment first to make the technology market ready. So we have money at Transphorm from venture capitalists, and from ARPA-E, from the Office of Naval Research, and from the Innovation Corporation of Japan, which is a Japanese sovereign fund. The most important thing that you have to do is you have to actually provide the performance at an acceptable system cost. That means a return on investment argument works with an industrial customer, does not work with a consumer very well at all. So basically, if you make something happen in this, you better have the system cost be actually at par with a silicon-based solution or preferably lower cost. So and as was alluded, the increased technology cost, because gallium nitride or silicon carbide or any other technology is more expensive than silicon, by definition it is. But it is defrayed by reducing the commodity cost, so less copper, less aluminum. It also is very important that the less you're dependent on copper and aluminum, the better handle you have on your pricing structure. I mean, if China's economy starts heating up, the cost of copper and aluminum just goes skyrocketing, and you can't change the price of your PV inverter. So your earnings are going to be dependent on macroeconomic conditions, and you don't have control over that. And so the less you're dependent on it, the better off you are. And the market needs to be ready. Making it easy to use is very important. I mean, you cannot make a customer study you can't give homework, to a customer. You basically have to make it just plug and play for the customer. It's real easy to use, important. And lastly, the market needs to be ready. In these very conservative markets, and they're rightly so conservative, I mean, for many reasons, safety being an important aspect, you need one person to actually change, and then a domino effect follows. So this is basically the market that we are playing in. And just a few things. If you go up in frequency, Rajeev mentioned this, if you go up in frequency, everything gets smaller because all electrical parts scale inversely with frequency. Higher the frequency, smaller the part. And you see on the left a conventional, what is an inverter with a filter, and on the right you see an integrated filter. And this basically was funded by ARPA-E, and that's a module with an integrated filter operating at 300 kilohertz. Now here's the product that came out of a lot of the work that we've talked about. This is the first gallium nitride-based inverter product, which is now going to be released in late 2013, this year, into the market. And what you see is a 40% volume reduction relative to a silicon inverter, and the efficiency has gone up by over 2%. It's at 98.2%. This is a solar inverter. This is the full inverter, not just the power electronics. This is DC in to AC out. And now that's remarkable. And what it allows you to do is make a very small solar inverter, which is fan-free. Because, again, as JB mentioned, if you are highly efficient, you don't dissipate heat. If you don't dissipate heat, you don't need a fan. So what you see is a small, fan-free, 4.5 kilowatt inverter that will be entering the market. Very excited about it. Also, what these power electronics does is that with these integrated filters, you get a pure sine wave that comes out of the power inverter, as opposed to that jagged wave you see on the top, which is a conventional power electronics with signal coming out of a silicon-based inverter. These smooth signals make motors more efficient. They actually impact the efficiency of the motor, because motors like smooth signals, not jagged signals. This is Lisa's slide, actually, effectively. You want to make adapters smaller and ultimately disappear. And I'll end with this. Data servers are a huge growing, data server farms are increasing rapidly. And efficiency savings in data server farms, is basically a bottom line advantage to companies that own data server farms. And for each 1% efficiency improvement in a typical data center, you save about $2 million in electricity cost per center. So that's another big advantage. Well, thank you for listening, and happy to take questions later.
Thank you. That was an excellent panel. I hope we're on the well on the way to making high-efficiency power electronics sexy, because that seems to be one of the issues. I wanted to sort of kick off the discussion by first asking Umesh and Rajeev if you could comment a little bit on the different sorts of chemistries that are out there, and do we have sort of clear leaders in this field at the moment? And should, those of us who went through the conversion from VHS to DVD, or, you know, these sort of epic conversions, should we be realizing that things are still settling out, or where are we?
Where to start? Because I know what you're going to say.
I was going to say let Rajeev start because he'll have a more unbiased view of this. Okay, anyway, there are, as far as I'm concerned, there are two real chemistries, as you call them, two materials that actually have promise. One is silicon carbide, and the other is gallium nitride. And the way I look at it is that the marketplace is, you can split the market into two. One is the enormous power required for a grid, and then there's power conversion for stuff which is 50 kilowatts and less. And in the 50 kilowatts and less, which is most of the market, I think gallium nitride is the dominant player. I'm pretty confident that that's not an unbiased view. I think we'll take over everything, but
Rajeev, will you give us a...
So I guess just to give you context, so in 2009, there were no companies selling wide bandgap switch transistors, right? So you could buy a diode out of a wide bandgap material, but you couldn't buy a transistor. I mean, today we've got more than a dozen companies. I mean, probably a dozen on the nitride side, easily a dozen on the silicon carbide side. So I think the world has really changed in terms of the transistor side. You know, I think if I look at the most successful device, it's probably the silicon carbide diode. It represents something like 80% of power supplies that go into servers.
yes.
And I think it's an important chemistry in that sense. I think there's something like 32 billion hours worth of
Yes.
actually field data on those devices, and they've been illustrated to be more reliable. I guess the other thing I want to complement that is that there are a lot of other new materials that people are investigating. Certainly ARPA-E has invested recently. In the last year, we've actually started looking at a lot of other new trajectories as alternatives to gallium nitride and silicon carbide that might have ultimate lower costs, things like aluminum nitride as a possibility, zinc oxide, things that might fundamentally be able to be grown differently in bulk. But I want to also add that if you look at a power electronic component, it's important to realize that, I mean, while we've been talking mainly about, I guess Umesh we've been talking about switches, I mean, equally important to the performance of the device, if I look at any innovation that's really come out on the product side, it's really been held up by 4 different things. And that's basically been the switch, the circuit design, the package, and the passives. And if I look at the passives, that's all new material. Today, all of the magnetics, all the transformers and inductors are only made out of ferrite and steel, right? And that's going to change. That's going to change dramatically. It's a little further behind in terms of investment because it's really something that's specifically targeted to the power sector. But there will be a large number of new alloys that come on the market, that are coming on the market now, that are really enabling a lot of these applications. I think even if to basically kind of realize the ultimate performance of gallium nitride and silicon carbide, I think it's well understood that we're going to need new magnetic materials, new passives to support that.
And just a small addition, I completely agree with Rajeev, but speaking as a Transphorm person, the only thing we can sell is stuff where we have done all the work, not only made the switch, but we've actually done the circuit design, we have actually innovated in the package, and then we sell the whole solution so that as far as the customer is concerned, it's basically a black box that is easy to use. So thank you for raising this issue. You just can't do one thing. Mm-hmm. You got to solve the problem for the customer.
And there are new materials in all those areas.
Mm-hmm. So it's this highly fluid sort of area that you're moving in your area, but then you're dropping it into big things like refrigerators that have to be able to run 24 hours a day for 10 years without hiccuping. And I wonder if, and cars are sort of another level of safety and performance. And I wonder if Hari and JB could kind of talk about, you know, if someone came to you with a perfect box that's going to give you an increase of 2 or 3% in efficiency in a transformer, what's going to keep you from throwing it right in? And how long an adaptation time are we talking about?
If I might start? Sure. I think it's a very important point that no technology stands in isolation. It's about how it plays with the rest of the players. And one of the areas, as I was talking about, is mechanical to electronic transformation. there's a lot of firmware and software and a lot of aspects which go in between, connecting the logic of what is happening downstream to what are you trying to do upstream with the power. And that, with the lack of standards, which the way some of our earlier colleagues spoke about with the Ethernet of things, the lack of standards, that interconnect and that code development is not been as fast as one should, one thinks. But the positive side, I feel, is as we have not done a great job with the technologies which are kind of commoditized to date, the barrier to jump the gun as new materials come up is actually going to be lesser. And that's a good thing, provided we figure out a way of working integrated across these subsystems in a better way.
And JB?
Well, I mean, if there was truly something that was 2% or on that order, it's a huge, value. We would work really, really hard to adopt that as fast as we could, and I think we kind of pride ourselves on trying to be the industry leader in rapid adoption of new technologies. That said, I think often what gets overlooked, and we are approached, I'm sure everyone's approached often by kind of new startups with new technology, the whole production and quality control all the way through the manufacture at scale is a pretty big challenge with power electronics, maybe less so with magnetics materials, but certainly with switches. And I think having people that can demonstrate how to partner or operate at really high volumes of production with very, very high quality is critical for us. We can't sort of get started and sort of adopt 25% of our products, then have some problem, then scale back, then wait and scale up. That gets to be a pretty big hurdle that has to be overcome.
And I think you mentioned at one point that the testing on the Volt, it took 4 years to introduce new components, so that even though possibly the Tesla is the closest thing to a computer that looks like a car, it takes a long time. You're still working with sort of automotive scale.
Yeah, I think 4 years is maybe too long. That's pretty conservative. In a technology.
It's a whole presidential term.
Yeah. Well, in a technology space where things are improving, so quickly, if you're forced to use technology that's 4 years old, you're inherently out of date. And that's, I think, a tough challenge for a lot of these incumbent industries when they find themselves in a space where technology is improving quickly. It's hard to be relevant and up to date and still be as conservative as they are used to being. So we have to find ways to accelerate that testing. And many of the parameters can get tested pretty quickly. You can do clever ways of figuring out what life will be under different aggressive operating conditions. So that's where the innovation comes, is how do you figure out a 10-year life in 1 year of validation.
Yeah.
But if you want to get into Ford's supply chain, right, to provide them the next inverter for their generation of cars, and that's a long period. I mean, that's a long qualification procedure. It's a long design cycle to basically enter. I mean, it's a different industry. It's a different kind of company, right? It's got a different design cycle. It's got a different scale that they're looking for, and so I think it varies dramatically from industry to industry. But I know that those are like getting into the big three, getting into the large product lines for the big three. I mean, just looking at their design, looking at the wins that our companies basically had to get in order to be able to be designed in was not. Those are long time scales, like 7-year time scales.
I think the challenge is that automotive companies, the big three or other European automotive companies are used to working on a time scale that's so much longer, and they're not used to working with power electronics or software or motors or batteries at all, for that matter. And they're sort of coming into it now and getting programs going at scale, but the supply chain is still the same supply chain that buys plastic bits and metal stampings and seats and tires and brakes. And those things don't innovate very quickly. You can afford to have a 4-year qualification time frame for a new brake component supplier, because it won't be that different 4 years from now versus what you bought 4 years ago. But with power electronics, I think, especially, and batteries as well, they've got to find a way to speed that up with technology-relevant things.
I think I was trying to comment on this coexistence of multiple technology life cycles, and I think that's going to be reality. And in our earlier work we did on security products, where you have so much of electronics getting onto your home lock, the lock may not be changed for 10 years, but maybe you might upgrade the electronics. And someone asked a question yesterday on design for sustainability, and that might be something we may have to kind of embrace, as to how do you co-design multiple life cycles that even through the development you're ready for new technologies. And I don't think we have a ready solution, but we've got to question our design practices in that regard.
Mm-hmm.
And if I just may add one thing, and to put a positive spin on this, I mean, Tesla is obviously, that leader, that the industry leader that can cause a domino effect. That I was referring to. But luckily, in power electronics, there are other markets which are very fast to adopt, and they are like gaming,
mm-hmm.
right? I mean, doing PC gaming, Xbox, all this kind of stuff requires efficient power conversion, and they are all about hot new stuff,
mm-hmm.
and you can sell. So, you got to find markets where there's less resistance, while you build on relationships and enter markets where there's more resistance.
I think this is such an interesting case of what happens when you bring something out of the lab and into the marketplace, and all of a sudden you have to think like a gamer, think like an HVAC guy, and I mean the span between those two industries is so enormous that it's really interesting. I want to get to audience questions in just a second. One of the things that's been coming up again and again through this conference is how do we sort of keep the efficiency and gains and the jobs themselves in the US? And there's a lot of different ways of looking at that. I mean, obviously, the more of these power electronics that are rooted in the US, we are saving that energy. But how does the job situation shake out, or do you have thoughts on that? And I bring this up in a way because we have been talking about solar and batteries. Batteries in particular, they thrive in countries that have a strong subsidy program. And so it's been hard to, there's a political component to some of the building of some of these technologies in the country. So maybe somebody can go with that.
Well, sure, I can jump in. I mean, at Tesla, we do build all of our power electronics in the US. It was not maybe the obvious choice in the beginning, but I think as long as you're trying to do fast innovation on the same product cycle and innovation into the manufacturing process as well, that really benefits you being close to your final product assembly and your customers, and where your engineers actually are. So I think that's probably the key is trying to make sure that we stay focused on the innovation more so than just reducing labor content. Labor content in power electronics is not a big driver in most mm-hmm. cases. Even especially in the newer materials, it's even less really pure materials content. It's more, sort of highly processed materials or software development. Those kind of things, are natural job creators right here. So I think, biasing products to really have more focus there is the key.
And essentially, you're embedding kind of service industry software within the electronics. In a way, you're creating a different sort of product than pure manufacturing.
Yeah, it's really, I guess, focusing more on the innovation and development, and those are in a lot of cases, I think, the really valuable jobs, and it's really what creates relevancy and keeps the product improving. That if you focus, more development into better software, that tends to increase efficiency a little bit higher, and it tends to, certainly have a product that can be more competitive.
All right, other thoughts?
So at RPE, we had an interesting perspective on this because our mandate was to basically support the U.S. economy and to support the jobs. And so one of the requirements that we had that was actually embedded in all of the contracts is that all the manufacturing for all of the power electronics across the several dozen programs that we supported all had to be done in the United States. And so all of those companies, Transphorm, Cree, all of those companies basically manufacture in the U.S. Those are all U.S. jobs. I guess the thing that I would stress is that there are a lot of drivers to basically making it so that continues to happen. So one of those drivers is the lead that the U.S. has, for example, in materials like silicon carbide. I mean, we have just an incredible lead. So even though you might buy a silicon carbide transistor made in Japan, the substrate was almost definitely made in the United States. So I mean, that lead is so phenomenally large that it's actually a strength that we can leverage on with the investment that we've been talking about in wide bandgap. I think the other things that, the currency fluctuations are non-trivial. I mean, if you look at Toyota, I mean, the investment that we made in APEI for their high power density inverter, that was basically matched by Toyota North America. And the reason for that is they wanted a supply chain that was local to be able to serve their market. They couldn't tolerate the currency fluctuations. It was really killing them. And so, you know, we're actually starting to see that their higher-end vehicles, like the Lexus, is basically moving to the U.S. for manufacture. That higher-end electronics is going to basically be moving here. So I think there's a couple of places, a couple of ways you can sort of see that things are going to happen locally in this area.
I agree, and actually to take off on Hari's point as well, you know, when the system innovators have to actually get all the subsystems talking to each other to basically get resonance between technology cycles and some other cycles within the system. So I think that what happens is that it becomes natural to actually keep the supply chain, the full supply chain, basically local rather than this the economics of the past in other materials. It might still work in other systems, but in this system, you got to really understand all the way from the material to the final packaged part, and then have the cycle of learning be implemented and have it implemented in the correct place. I mean, if I buy something from company X and buy something else and then ship it to company Y and then bring it to company Z, and if the final product screws up, where is the problem? And you can't even solve it. So it's really important to have that full supply chain. So I'm very optimistic of this particular industry having a very large US presence.
Interesting.
Adding to that, I think it's one of the things to work on further is the availability of talent pipeline.
Yeah.
Because clearly, as people alluded earlier, this is not as sexy, but I think if the energy is the future and how we can have more trained power electronic engineers in our pipeline in the country is extremely critical.
All right, that seems like a good note to go to the questions from the audience. I'm not sure who was there first.
That's okay, it doesn't matter. I take it.
Okay.
We heard earlier in this conference about great progress that's being made in batteries, and particularly the team at A&L has come up with some new advanced chemistries for lithium-ion batteries. And a year ago, NVIA, I believe, announced they had a 400 watt-hour per kilogram lithium-ion battery. Last fall, California lithium-ion battery said they had a chemistry that was similar to A&L's, and they were at 525 watt-hours a kilogram. And I believe I've read that both of these companies said that the cathode and anode materials that they were developing were going to be drop-in materials that could be dropped into existing battery processes. And as Mr. Straubel pointed out, Tesla tries to adopt things very quickly and accelerate things, and I was hoping someone could comment on what aspect of drop-in I don't fully understand.
Well, I think it's always tricky to go from a press release on a given particular material property or parameter all the way to working cell and battery pack. Believe me, we would be the first to try and adopt something like that as fast as we could. There'd be no reason to not want to do that. The challenge is to make sure that it really meets all the other metrics that are equally critical, and not to get us too far off the power electronics track, but batteries and cells especially have so many figures of merit. And what I've seen many times is that there will be a massive increase in one figure of merit that gets marketed, discussed, promoted. We have 100 times better power. How could you not want to buy this? Well, oh, by the way, it's 1/10 the energy. Or we have a 50% improvement in energy, but it has 100 cycles. So it's you really need to look at the entire set of characteristics. And in many cases, if you hear a press release and then you don't see it show up in a product, what probably happens is that you didn't have a balanced set of improvements that really made it compelling as a value. And we look at all kinds of new materials all the time, all different startups and labs, and it tends to unfortunately be incremental. Maybe 7–8% improvement per year by the time you get to a whole system level in a battery pack that can go into a vehicle or a stationary application.
It's also usually true that the higher the energy density of the battery, the more careful you have to be about the battery management. And at some very first principles level, there's a lot that we don't know about batteries. I mean, understanding dendrites, understanding like all the different, how to balance all the reactions and electrochemical reactions that are happening. I mean, there's a, I mean, we about a year and a half ago basically invested, $25 million in just understanding how to basically measure the performance of a battery and feed that back into a model so we actually knew what was going on. And there are virtually no battery systems that we understand so well that we can predict what the life of the battery is going to be. And so, you got to, the reality is a little harsh in terms of where we are.
That's another sub-theme of the conference is the unreliability of the things people say about batteries. Please, give us a question.
First of all, thanks to Dr. Mishra for showing and sharing that slide, how much energy loss they can save in electronics. And Dr. Ram's information about introducing new materials, and I'm thrilled to hear that. The last material that I knew for soft magnetic materials was invented over 50 years ago, which was called met glass. And last 50 years, there's no new material for electrical machines or power systems. That is the basis of my question.
But that's not totally true. I mean, there's been a lot that's happened in the last 5 years, but you're right, it's been much slower than innovation on a lot of the other sides.
Not in use. They're all probably in the development stage, but not to the extent that they have been used in commercial products. That was my intent. Of course, I know a lot of materials which I have used in several other applications which probably the world doesn't know to some extent. And that is primarily because we all, as an electrical engineer, know that magnetic materials are totally different than, they have different characteristics, which is non-linear characteristics. That means it is very hard to predict.
I'd like you to move to your question quickly because we're running out of time. Okay. Sorry.
So we are dealing with non-linear materials, and my question here is, of course, the emphasis has been so much on electronics, and of course the losses in electronics, but one of the critical components is electrical machines, whether it's generator or a motor. Either way, you need something to improve the efficiency of electronics. And Dr. Mishra mentioned that what he does in electronics, his devices improve the efficiency of the system, so primarily because it affects the waveform, which affects the output and saves in the motor. So my question is, when are we going to focus about the efficiency on the electrical machines?
Okay. Is that in anyone's bailiwick here?
We do spend a lot of time, focusing on electric machine efficiency. Absolutely, it's we actually have an integrated system that's the control of the electrical machine, the gearbox, all of it is in one unit in the car. I guess my view on where that's headed though is that the electrical machine parameters are tending to be more and more commoditized. The parameters of just an electromagnet basically sitting there. It's hard to improve it hugely. You've got copper and you've got magnetic material. Then the control and the power electronics is improving quite rapidly. So I think it's critical to think of it all as a system and to understand the parameters that you're trading off against. But more and more I think you're going to see less of a typical kind of standalone electric motor and more of a set of electromagnets that can get controlled very independently, which in and of themselves wouldn't really make much of a motor.
So one thing I want to comment is, if I look, so most people who design machines basically design machines using magnetic materials that were invented, again, a long time ago. So there's been a lot of work done in soft magnetic materials in the last 5 years. And no one's made a machine using any of those materials. So there are materials that have twice the saturation magnetization, right? 2 Tesla instead of closer to a Tesla, have much lower eddy current losses because they're much less conductive, have much lower hysteresis losses because they're actually softer magnetics. So there are all these characteristics that we know would make a much better motor that could actually leverage, you could do all sorts of things to make higher density motors out of them. I don't know anyone who's really investing a lot of energy to basically translate new materials that exist on the soft magnetic side into machines. I think it's something that could be done, and it's actually something that we've actually had a workshop about 2 years ago, kind of looking at that as an area of investment that a lot of companies, Hamilton Sundstrand, a lot of these companies understand the design space, but really are not investing in materials. And so that material investment that's basically starting to show up in inductors and transformers really is something that basically people need to look more seriously at. And it's kind of outside, we talk about vertically integrated. There's vertically integrated companies that know packaging and systems and transistors. I don't know of example of a vertically integrated company that knows packaging, materials, and magnetics. Right? The magnetics is always something that you get from somewhere else. And so it easily is the bottleneck for a lot of systems.
Okay, I want to move to the last question. I'm sorry, you'll have to take it up outside.
I can tell you some of the new materials
I
that
think
I've used.
you have to take it up outside, sir. Please.
Yes, well, with solar cells using gallium and LEDs using gallium and now power electronics and transformers using gallium, will there be enough gallium available as a material to be able to accomplish as much as what the demand for the market could require?
Yeah, luckily the answer for that is yes, because we don't actually mine the gallium. It's actually, gallium is a byproduct of aluminum manufacture, and it actually is in the slag in aluminum refining. So it's a byproduct. So a good way of looking at it is always look at the price of gallium, and the price of gallium has remained pretty constant with an increased use of gallium, because actually the recovery is pretty good. You can mine gallium as well, but there are alternate sources.
It's also only 2 to 5 micron film of gallium nitride on a silicon substrate. So the vast majority of the material, while the gallium nitride is doing all the work, is actually still silicon.
So we don't have to do multiples times more gallium supply to accomplish the demand for these type of...
That's right. It's limited use of the film because it's thin, and an access to gallium through direct mining and recovery from aluminum refining.
Thank you.
Thank you very much. This has been a very interesting conversation, and thank you to the panelists. If there's anyone out there thinking of going into high efficiency power electronics, I hope you do. And we'll turn it over to the organizers.
Thank you.
Thank you.